Okay, so I want to work the problem that we were working on at the end of class on Wednesday for this video, and then I'm also going to show you a couple of new integrals in section 5.7 so that we can work plenty of examples in class on Friday. So if you look at this integral that we were working, a lot of you did a really great job of finding u, and u was 1 plus 2x cubed. A couple of you struggled a little bit with that and chose maybe only a portion of this. But then if you only choose a portion of that, when you think about actually trying to solve the problem, you still have like a 1 plus u inside of the fifth. So generally your key big thing, remember, is you want to choose something inside the parentheses. So you want to choose this piece. Don't do it to the fifth because that's going to make a really complicated derivative. So if this is your u, your du is going to be 6x squared dx. Okay, so when we're starting to rewrite this, this is going to be the integral of 1 plus 2x to the third, so that's u to the fifth, so that takes care of this part. And then what's left is just x squared dx. So x squared dx is what we need to solve for here. And so what we really need to do is divide both sides by 6. And so that says du over 6 is x squared dx. And that's what's left over in our integral. So that's what we're going to put here. So that's du over 6. And now, since this is an integral that involves bounds, these bounds are originally 0 and 1, so we're going to convert our bounds. So if we plug in 0, we get 1 plus 2 times 0, which is just 1. So the bottom bound here is 1, and if we plug in 1, we get 1 plus 2 times 1 cubed, which is 1 plus 2, which is 3. So this is really just now the integral from 1 to 3. You can take the 1/6 outside and you have u to the 5th du. And if you integrate that, you're going to get 1/6 times 1/6 u to the 6th. That was another big mistake that y'all were making, was forgetting how to integrate u to the 5th. So when we integrate, we add an exponent. So just don't forget to add, not subtract when you integrate. And we're going to evaluate that from 1 to 3. And so a lot of you got this. It's 1 over 36, 3 to the 6th, and then minus 1 to the 6th. And there's a nice decimal answer or a fractional answer. I think if you want to write it as a fraction, it's 182 over 9. Simplified. One other thing I did want to point out, a lot of you on this step right here, you still had some x's in here. So just remember, your goal here is to get rid of all the x's. So if you have an x in your problem still, then you're not finished substituting and you didn't do the substitution correctly. So you might want to go back and fix that. Okay, the rest of this video I want to talk a little bit about 5.7, which is really very similar to what we were just doing. It just introduces a couple of new integrals, possibly new, maybe you've seen them before. I'm going to wait on this ln of x deal. I'm going to do that in class, but what I did want to do is go over these formulas with you. So the first one, these three integrals are actually things you probably know, and for me the one that's really obvious is the middle one. And the middle one, the integral of 1 over 1 plus x squared. So hopefully that looks familiar to you. That's really, change my pen here, the integral of 1 over 1 plus x squared dx. And if you remember, that's the antiderivative of tan inverse or arctangent. And then similarly here, this is the integral of 1 over the square root of 1 minus x squared. And just to keep things with the positive version, we use sine inverse for the antiderivative here. I guess you could also use negative cosine inverse, but that requires a little bit more work. Next is the integral of b to the x dx, and here we want to integrate this. So if you remember, the integral of e to the x is e to the x. So similar for b to the x. So we definitely get the b to the x like you would get if you were doing the antiderivative of e to the x. But if you remember, if you take the derivative of b to the x, you multiply by the natural log of b, by the base. So when you take the derivative, you multiply by the natural log of b. So when you take the antiderivative, you're going to need to multiply this by 1 over the natural log of b, and then add your c. So these are three sort of new. Okay, so those are the three sort of quote-unquote new integrals, but in fact they're really just basic antiderivatives of things we already knew how to take the derivative of. But I did want to look at these two examples on the bottom of this page. So looking at these two examples, we have the integral of x squared plus 1, which hopefully you recognize as just being inverse tangent from above. You can also write that as arctangent, of course. These are equivalent, and you can write either one. But keep in mind that this is not ever equal to 1 over tangent of x. That's not the same thing. So don't ever write this. This is terrible. Just keep in mind that tangent inverse and arctan are the same thing, so you can use either of those interchangeably. So that's the integral of 1 over x squared plus 1. Notice this next integral over here, which looks almost identical to that one, but it has an x on top. And so you'd think maybe it's just tan inverse of x. So we need to figure out a way to integrate this that makes sense for this problem. So clearly it's not just tan inverse of x because there's that extra x on top. So we have to think about what other integration techniques we have. So it's not a basic integral and it's not one of these ones we just learned about. So the only other method we currently have is substitution. So we could think a little bit about a way to do this substitution. And if I look at this problem, there are a few options, right? If we think about it, we could use x, or we could use x squared, or we could use x squared plus 1. And remember, the whole idea of substitution is to help make our integral an integral that we can actually integrate. And if I let u be all of x squared plus 1, then I think that makes my integral much easier to evaluate. So if u is x squared plus 1, I take the derivative, I get 2x dx. So then it looks pretty close to what I actually have here. In my integral, I'll have the integral, u is in the denominator. On top, it looks like I have x dx, which would be this piece of my derivative, so I would need to divide both sides by 2, and I'd get du over 2. So you can put that on top, or you can put it over here, depending on your algebra skills and what you feel comfortable with. So that would be our integral that we're going to integrate. And the first thing I'll do is take that 1/2 out, so that's not as confusing, and I just have 1/2 1 over u du. So then it's 1/2 natural log, absolute value, don't forget that, of u plus c, and in this case the u is x squared plus 1. You don't actually need the absolute value signs here, obviously, because that's always a positive number, but it's always nice to put them just in case so you don't forget them in problems where you definitely need them. So I hope these two examples kind of show you how much more complicated a problem can get by just a slight alteration. So just without the x on top, it's just a basic antiderivative, but with that x on top, it immediately turns into a substitution problem. We'll look at many more examples in class on Friday of how to do this, and also many other substitution problems.